Determining the percent yield of a reaction. The percent yield is what tells you how good a reaction went or how much product you're actually getting from a reaction. The closer the percent yield is to 100, the better the results for your reaction. So I have here some definitions. First, we have the theoretical yield. And the theoretical yield is a number that you can actually calculate before even doing the experiment. If you know the amounts of reactants that you're using in the beginning of your reaction, you can actually use the initial amounts of reactants to calculate what's the theoretical yield, which is an amount of product, or how much of a specific product you can get from your initial amounts of reactants. The actual yield is an experimental amount. So once you perform your experiment, the actual amount of product that you're getting from your chemical reaction, that is the actual yield. So to calculate the percent yield, you have these two amounts. You have your actual yield, which is the actual amount of product that you're getting, divided by the theoretical yield, which is that amount of product that you're estimating you're going to get. You're calculating. It's not an estimate, it's an actual number. That amount of product that you're calculating that you can get from the initial amount of reactants times 100, that will give you the percent yield. The limiting reactant, like usually when you have a chemical reaction, you will have more than one reactant, okay? Maybe 2 or 3. Out of your 2 or 3 reactants in your chemical reaction, one of them is going to be used up entirely. So you have reactants in excess, and you have an amount of reactant that it's actually going to determine how much product you can get at the end of your reaction. So the limiting reactant is the one that is going to be used up entirely, and it's actually the one that is going to give you how much product you can get at the end. And you will see with the example. So I have here a diagram of the steps that you need to follow to get your theoretical yield. You're starting with the grams of your limiting reactant or amount of your limiting reactant in grams. The first thing is converting those grams to moles. To convert grams to moles, you have to divide by the molar mass. Once you have your moles of the limiting reactant, you can convert those moles to moles of product using stoichiometry. And stoichiometry is just the ratios, the molar ratios that you have in a balanced chemical equation. So down here, I have the actual reaction that you're going to be doing in this experiment. The coefficients are the numbers that you have in front of. So this reaction here is telling you that you have 2 moles of aluminum reacting with 2 moles of potassium hydroxide, and you also have reacting 4 moles of sulfuric acid, and then you have 22 moles of water. All of the things that you have on the left side of the arrow is here. Everything on the left side of the arrow are reactants. So you have reactants in this equation. You have the aluminum, potassium hydroxide, sulfuric acid, and water. Everything that you have on the right side of the arrow, it's a product. So you have here hydrogen gas, and then I have down here underlined with a pink line 2 moles of alum. So all of that formula that you have there, KAl, SO4, 2 of them, and then 12 water molecules, all of that is your product alum. So you can see that I have a number in red in front of aluminum and a number in green in front of alum, your product. That right there is your molar ratio. Look, for every 2 moles of aluminum that are reacting, you're getting 2 moles of alum, which is your product. So I have here 2 moles, and right there 2 moles. So that's your molar ratio. Every 2 moles of aluminum is giving you 2 moles of product. In this experiment, the limiting reactant is the amount of aluminum that we're using to start the reaction with. We have potassium hydroxide in excess, sulfuric acid in excess, and we have an excess of water. So we can actually calculate the amount of product that you can get, or that maximum amount of product that you can get from your initial amount of aluminum. The molar mass of a compound is the sum of all the molar masses for everything that you have in that compound. So I have an example here, and the compound, it's copper sulfate pentahydrate, because copper sulfate has 5 water molecules as part of the crystal structure of the compound. So I have all of my numbers written down for all the molar masses of every um, element that you have as part of the formula of the compound. So the 63.55 grams per mole is the molar mass of the copper. Then you're adding to that one 32.06 grams per mole, which is the molar mass of the sulfur. And then you have 4 oxygens, and the 4, which is a subscript in your formula, I'm putting that one with the blue arrow, and that's the 4 that you have in front of the 16. And 16 is the molar mass of the oxygen. Since you have 4 oxygens, that will be 4 times 16. So all of that I have in the first parenthesis is all of the molar masses that you have in the copper sulfate. Then I'm adding plus. You have a line in red that represents the 5 water molecules that you have, and then you have in the brackets 2 times 1.008, which is the molar mass for hydrogen, and that's times 2 because you have 2 of them, plus 16 because you have 1 oxygen in the water molecule. So adding all of that together gives you 249.69 grams per mole, which is the molar mass for the copper sulfate pentahydrate. So that's an example on how to calculate molar mass. Now I have a generic reaction here. So you can see that the reactants are on the left side of the arrow, then the products on the right side. You have different numbers in your reaction. You have subscripts, which are specific for an element in a compound, and then you have coefficients, which are in front of a formula. So the numbers that you have in your equation number 2 in red, that's a coefficient. That coefficient is for your reactant A. Then for B2, the second reactant, there's no coefficient, so it means that you have a 1. And then on your product side, you have a 2 in green. That 2, it's the coefficient that you have for your product AB. So you have on the right side molar masses listed. You have molar mass for A, that's 26.98 grams per mole, and molar mass for your product AB, 57.01 grams per mole. So we're going to use all of that information, including the coefficients that you have in the reaction and the molar masses, to do the calculations that I have listed here as A, B, and C. So you're starting a reaction with 5.33 grams of A, which is a reactant. And the first thing that you have to do is to find out how many moles of A are you using. So converting grams to moles, there's always the same thing. We always do the same thing. Converting grams to moles means that you have to divide by the molar mass. So you have 5.33 grams of A, and you want to know how many moles, or that equivalent amount in moles for 5.33 grams of A. So I'm starting with the given amount, which is what I have highlighted in pink, 5.33 grams of A, and you want to know how many moles is that. The molar mass of A is listed right here. That's 26.98 grams for every mole. So if you have 26.98 grams of A, what you have, it's the equivalent amount of 1 mole of A. So you don't have 26.98 grams. What it's given is 5.33 grams of A. So you want to know how many moles you have in that specific amount of grams. So 5.33 times 1 divided by 26.98, that's 0.198. So if 1 mole of A is the same as 26.98 grams of A, when you have 0.198 moles of A, that equivalent amount in grams will be 5.33 grams of A. So for the second problem here, what you want to know is, okay, how many moles of AB, which is your product, you can get if you start your reaction with 0.198 moles of A. So if you have 0.198 moles of A, and now you're trying to determine the amount of product that you can get, which is your theoretical yield. That's what we're actually doing. You have an amount of reactant given, that's reactant, and you want to know how much product AB you can get with that specific amount of your reactant A. If you look at your generic equation up here, look, every 2 moles of A that you have is going to give you 2 moles of your product AB. So this is what the reaction is telling you. 2 moles of A, it's enough for you to get 2 moles of AB, assuming that you have enough of your second reactant, which is your B2. So the actual initial amount is not 2 moles of A. With 2 moles of A, you know you can get 2 moles of AB. But what you have is 0.198 moles of A. And you want to know how many moles of AB you can get with that initial amount of your reactant. So for this part here, when you're converting moles of A, which is the reactant, to moles of AB, which is the product, you have to use the coefficients that you have in your chemical equation. Look, that 2 in front of the one that I have in green in front of AB, that means that you have 2 moles of AB. And I'm writing that one on the top part of my conversion factor because that's what you're trying to calculate. Whenever you're trying to calculate something and you're using a conversion factor, what you want to get has to be on the top part of your conversion factor. Now, the given amount or the initial amount that you have is your moles of A. So 2 moles of AB, that goes over 2 moles of your reactant A. So my numbers here are numbers that I'm taking from the balanced chemical equation up here. So every 2 moles of A, for every 2 moles of A that you're using in your reaction, you're getting 2 moles of AB. So now your moles of A are canceling out with moles of A. Whatever amount you're getting will be moles of AB. That's the number of moles of product that you can get. So that will be 0.198 times 2 divided by 2. That's going to give you 0.198. So if with 2 moles of A you can get 2 moles of AB, with 0.198 moles of A you can get 0.198 moles of AB. So the next one is to find out the amount that you have in grams. When the problem is asking you what is the mass of AB, you're trying to calculate your theoretical yield, but now instead of having your theoretical yield in moles, which is what we calculated in B, you're converting moles to grams. That's what we're doing in letter C. So the amount of AB that you have in moles, 0.198 moles of AB, you can convert that amount of moles to grams multiplied by the molar mass. So the molar mass of AB, if it's 57.01 grams for every mole. So unit of mole is canceling out, and what you're getting is the same amount, but instead of units of moles, you're going to have units of mass. So 0.198 times 57.01, that's 11.3 grams of AB. So 0.198 moles of AB equals 11.3 grams of AB. So it's the same amount. You have amount of product that you can get with your initial amount of reactant, which was 5.33 grams of A. The only difference between B and C is the unit that you have. Both of them are representing the amount of product that you can get. Letter B is your amount of product in units of moles, and then letter C is the amount of product in units of grams. So percent yield, you have your equation, actual yield divided by theoretical yield times 100. The given number here as part of your problem, that's the actual yield, is the amount of product that is being obtained. So you have an initial amount of reactant that you know, you're using that amount of your reactant to do your reaction, and then at the end of your experiment, you're getting your amount of product. So the amount of product for this example is your 8.22 grams. Okay? So that's your actual yield. The theoretical yield we calculated in grams, and we obtained 11.3 grams. Okay? That's the amount of product that you can get with your initial 5.33 grams of your reactant A. So your initial amount of your reactant A is giving you your theoretical yield, which is 11.3 grams. Whenever you're trying to calculate the percent yield, you have to make sure that the actual yield and the theoretical yield, that you have the same unit for both numbers. We calculated theoretical yield. You have two amounts. It's the same amount but with different units. You have your theoretical yield as 0.198 moles of your product AB, and you have in letter C your 11.3 grams. Those two amounts, they represent the same thing, the theoretical yield, just with different units. Since the actual yield here is given in units of grams, You should use your theoretical yield also in grams so your units will cancel out. So you can calculate now your percent yield. So 8.22 divided by 11.3 grams, your units are canceling out, and that will be 72.7%. The first thing you're going to be doing for this experiment is finding a piece of aluminum. You're going to clean your piece of aluminum using sandpaper. So just scraping the surface of your aluminum just to remove the wax, and then you're going to cut your aluminum into small pieces. And your pieces, they should be smaller than a dime. So you're going to cut all of your piece of aluminum, big piece, into small pieces. You're going to have a dry beaker. You're going to put your dry beaker in the mass balance, and you're going to copy the mass of your empty beaker and write it down in your lab manual. Now you're going to start adding pieces of aluminum, the ones that you have. You're going to start adding pieces of your aluminum inside of your beaker, and you will see that the mass of your beaker will be increasing as you keep adding your aluminum. You're aiming for the mass of your beaker to go up by about 1 gram. So if your initial mass for the beaker empty was 25, you're going to continue adding aluminum until that number goes to something close to 26. You don't need exactly 26. You don't need exactly 1 gram. You need something close to 1 gram. So you can have a little bit more than 1, a little bit less than 1, but something that is close to 1 gram. So you have the mass of your empty beaker, copy all of the numbers, and now you're adding aluminum until that number increases by about 1. You're going to copy the exact mass that you have after adding the aluminum. So you have your two numbers, empty beaker, and then you have the beaker with the aluminum. Now you're going to go back to your bench and you're going to add 40 milliliters of distilled water to the beaker with the aluminum. Measure those 40 milliliters of distilled water using a graduated cylinder, not with the beaker. Use a graduated cylinder, measure your 40 milliliters, and then transfer that into the beaker with the aluminum. Find a piece of labeling tape and put your name and the name of your partner and put that labeling tape on the beaker. Go to the fume hood, and in the fume hood you will find a beaker containing potassium hydroxide in a graduated cylinder. Use the graduated cylinder to measure now 30 milliliters of potassium hydroxide and transfer that into the beaker with the water and the aluminum. So now you have your beaker that it's labeled, it contains the aluminum, the water, and you're adding the potassium hydroxide. You don't need your own graduated cylinder. There's one in the fume hood. You have to make sure that you're wearing gloves and you're wearing your safety goggles. And you can leave the beaker in the fume hood. The reaction will take about 1 hour, probably not the entire hour, but something close to 1 hour. We can determine if the reaction is over by looking at the beaker. As soon as you add the potassium hydroxide, your reaction will start and you will be able to see bubbles of hydrogen forming. Once the reaction is over, there's no more bubbles forming in your reaction, and that's how you can determine if the reaction is over. Once the reaction is over, you're going to add now sulfuric acid. Before adding the sulfuric acid, we need to filter the solution so we can remove any impurities that are left behind after you add the potassium hydroxide to your beaker. So you need to set up your filter paper using a funnel, and you have your reaction. So you're going to filter your reaction through the filter paper that is in a funnel into a clean beaker. So your reaction will look like dark with like grayish particles inside, and then after you filter that reaction, it should look clear. If you still have some grayish or small particles inside of your reaction, filter the reaction again. Take a new filter paper and do the same thing again until it looks clear. Now we're going to add an indicator, okay, and the indicator is going to change color once your reaction goes from being basic to acidic. So potassium hydroxide, it's a base. So right now what you have is a basic reaction. When you add your 10 drops of methyl red, that's the indicator, your reaction will look yellowish because you have something that is basic. So this is a recommendation just to put paper towels on top of the bench. If you spill some sulfuric acid, then it will be contained by the paper towels and won't be like on top of the bench. So put some paper towels, 2 or 3. Place your beaker with your solution containing the aluminum after filtration, and then you have another small beaker with about 75 milliliters of sulfuric acid. The sulfuric acid will be on the fume hood. So you have your beaker with the sulfuric acid, about 75 milliliters of it. You need a medicine dropper so you can start adding your sulfuric acid into the beaker containing your solution. So it says here that you should add like 1 milliliter at a time while stirring. So you're going to be using a glass rod to stir. So what you're doing is mixing the acid that you're adding with the solution that you have. So we're not actually measuring 1 milliliter. You're going to take a medicine dropper, you're going to fill it entirely, and then you're going to add that amount into your beaker with the reaction, and you're going to stir. So one of you should be adding the acid, the other person should be stirring. You don't have to stir super quickly. You just have to make sure that you're stirring and that you're mixing the acid with the reaction. So one full dropper, you're going to empty that full dropper at once into your reaction. You're going to take a second one and you're going to keep repeating that. So you're going to continue adding the acid in the same way, one full medicine dropper at a time, until your reaction looks pink and clear. So in the beginning, you have a yellow reaction. You're adding your indicator, it's basic, it looks yellow. Once you start adding the acid, your color is going to start changing. The color will become pink, but it will look cloudy. Okay, in the beginning, it will look cloudy, and the more acid you add, your reaction will become clear. It's still pink, but you will be able to see through the reaction. So once your reaction is pink and clear, now you're done. Now we have to wait until next week so we can actually get the product from your reaction. Make sure that you label your beaker with your name and your partner's name, and there's going to be a tray for your reaction, for your beaker to be placed on. So I will let you know where the tray is in the beginning, so when you're done you can place your beaker with your label on that tray. After you're done with this, clean everything, return everything to the original location, and that will be it for this part of the experiment.